Previously, we've seen that a set of orthonormal vectors has some very nice properties. So just as a reminder, if I have a set of vectors, say q1, q2, all the way to qn, this is an orthonormal set of vectors if different vectors are all orthogonal to each other, so that means if I take two different vectors, qi and qj, and take their dot product, I get 0, right? That's what it means to be orthogonal. And also, all the vectors are normalized. They're all unit vectors. Which means the norm of any vector is 1. But important for our purposes, it also means that if I take the dot product of a vector with itself, I get 1. Right? Because remember, the dot product of a vector with itself is just the norm of the vector squared. Okay? So what we're going to do is we're going to explore this a little bit. What if we use an orthonormal set of vectors as the columns of a matrix? Okay? So let's let Q be a matrix with an orthonormal set of columns. Okay? And let's assume this is a square matrix. So n rows, n columns. So what can we do with this? So observe the following. Very important fact. Let's take the transpose of Q and multiply by matrix Q. Okay, so that means Q transpose, all the rows become columns, all the columns become rows. So column 1 becomes row 1. And this column actually flips on its side, so it's the transpose, right? And column 2 of Q becomes row 2 of Q transpose, and so on. And then this is matrix Q. Okay. Now, if I multiply these together, then let's just do it row by row, column by column. Okay, so let's take first row of the first matrix times first column of the second. Now that's going to be the dot product, right? So if I take the dot product of Q1 with Q1, because it's an orthonormal set of vectors, because the vectors are normalized, or unit vectors, the dot product of a vector with itself is just 1. So the entry in row 1, column 1 is 1. But all the other entries in this column, if I look at the dot product of any other row with that first column, because the subscripts are different, because it's an orthonormal set of vectors, the dot product of these vectors will be 0. Okay? And it goes all the way down because for all of these, the vectors are orthogonal, and so their dot product is going to be 0. Okay? So that's column 1, but we get something similar in column 2. Okay? Now, this first entry, the indices don't match. right? So these are orthogonal vectors. If I take their dot product, I get 0. So when I multiply these, I get 0. But in the next row, now the indices do match. So I'll get vector q2 dotted with vector q2. Because it's a unit vector, that will just be the vector of length. Or I'm sorry, I just get 1, the length of the vector. And that's the only non-zero element in the column. And I could continue doing that for every column. And what I end up getting is the identity matrix. In this case, the n by n identity matrix. Okay? That tells us something really interesting. It's this really interesting observation that if I have Q and it has as its columns an orthonormal set of vectors, then the transpose of Q is also the inverse of Q. Okay, and because of that, this also is going to be equal to QQ transpose. Remember, if vectors are matrices are inverses of each other, they do commute. Okay, so we could summarize these results with the following theorem. The following conditions are equivalent for an n by n matrix Q. Q is invertible, and the inverse of Q is the same thing as the transpose of Q. That's the case that we just saw, right? And we got there by setting the columns of Q and making sure they're orthonormal to each other. And it turns out, because, as I said, because Q transpose times Q gives me the identity matrix and their inverses, I'd also get the same thing with QQ transpose. And what that last observation shows is that the rows of Q are actually also orthonormal. So these conditions are all equivalent. Okay. It's a very special type of matrix. We call it an orthogonal matrix. An orthogonal matrix is an n by n matrix that satisfies any one of these conditions. And because these conditions are equivalent, if you satisfy one of them, you satisfy all of these conditions. Okay. So an orthogonal matrix, probably the easiest one to use to test, is a matrix is orthogonal if its inverse is its transpose. So, for example, if you wanted to test if a matrix Q was orthogonal, multiply it by Q transpose. If you get the identity matrix, it's an orthogonal matrix. If you don't get the identity matrix, it is not an orthogonal matrix. Okay? But if it is an orthogonal matrix, these other conditions also hold. The rows are all orthonormal to each other. The columns of the matrix of an orthogonal matrix are all orthonormal to each other.